So I realized that probably the final part yesterday was a bit fast, maybe, or unclear. So I'm gonna test you. So suppose I have a system which is an Ising dimer. So I have two spins in a magnetic field, and there's a little bit, at least, of interaction between the two, Ising interaction. So I have these two spin, and they interact. And now what? Doesn't matter. You can take it to be positive. So now I connect one of the spins to a reservoir at 0 temperature with an interaction which is sigma x times some operator of the bath. I don't care exactly which one, as long as the conditions for all of this to work are satisfied. Now, what shape do you expect the dissipator of the Lindblad master equation to have? So if I wrote something like this, would you think that this works? Yes, so that was the message. Indeed, the problem here is that this is the correct jump operator at j equals 0. So of course, then the two are independent, and if you couple just one of them, they also behave independently in a dissipative sense. The true one is actually, let's say, an addressed version of this, just to give you an idea of the kind of problems that you have if you use the wrong jump operators. Yes. So this is a simulation of this dimer with Q-tip, because well, you can do it analytically, but it's a bit long. So this is the energy as a function of time. The blue curve, in the blue curve, I use these dynamics, in which the jump only acts on the first. And in the orange curve is the one with the actual projected object, which is something. Actually, it turns out you need 2 jumps, because this is a 4-level system, and you have 2 transitions that that are important for at 0 temperature. So the true jump is something like, with coefficients, something like this. So it acts non-trivially on both spins. So I mean, this is the kind of problems that you have here. Essentially, I don't know if I said the green curve is the actual ground state energy. So the local dynamics is not thermalizing your system correctly, and it can go even, I mean, even more absurd, because in the case of the local dynamics, you don't even get a pure state. So really, this object is not doing the proper job regarding to thermodynamics. So this is an example. And okay, in this case, I just had fun with doing the projectors the projections by hand. I mean, it's doable, especially if you have numerics on your side. Okay, because again, the one thing that's often not well appreciated is that this formalism ensures thermalization, of course, if the right conditions, if you start with a bath at thermal equilibrium. So this is was just a good a reminder of this. Okay. So yesterday I derived the Redfield equation. I think this afternoon I'm gonna go directly to Lindblad with this. For now, I'm gonna give more details on the conditions for Markovianity. So yesterday afternoon, I commented on all this jump operator stuff. So essentially, let's say the input for this thing is that you need to know how you need to know the dynamics of the system alone. Which is, I mean, it's not so difficult if you have, 2 spins, but maybe if you have a many-body system, then it becomes problematic, unless, of course, it's a free system. Now we are going to look at this object more, which means looking at the properties of the bath. So first of all, the ingredients that we need are the correlation functions of the B operators in the bath. And by the way, yesterday I've shown you as an example the kind of spin boson model. So spin in contact with a reservoir of free bosons. But actually in this formalism, the bath could also be interacting. As long as you're able to compute this object with whatever means you have, you can apply this. The bath can be anything essentially, as long as that correlation function has the right properties that I'm going to show you. So, okay, let me just take one correlation function with just one operator. Just for simplicity, again, if the initial state of the bath is not an equilibrium state, this works the same, but you need to use explicitly 2 time indices. Now, first, let's say, implicit assumption is that this thing should go to 0 in time, which means that the bath must be big enough. Because otherwise, for a finite bath, you have recurrences, and this object is going to decrease in time, stay small, but then it will have peaks and come back. Now, when this happens, then the approximation leading to this fails. This is a form of memory of the bath. So the perturbation due to the system at a previous time propagates within the bath, bounces back, and comes back at the system. So let's say these dynamics can only work here. So between up to the first recurrence of the bath. Generally, the recurrence time is exponentially large in the number of components of the bath. So let's say this is a very mild assumption in practice. But if you want to consider small baths, then this is a possible issue. I'm assuming that you... It makes more sense if the system is smaller than the bath, but in principle, you can take the thermodynamic limit also in the system. Well, in principle, you can. From what I'm going to tell you, I'm not sure that that this formalism applies if you do that, though. Yeah, but okay, true. But this is a very, you know, it's a bare minimum condition. If you violate this, then there's not much point in trying to approach the problem with this formalism. So ideally, the bath should be a continuous system with a continuous spectrum. And in, yes.
I was wondering if you can, just looking for the models that you are using just for the system, interacting in the bath, if you always expect this kind of memory effect, or in which case can you expect it or not, or you need to do your calculations too?
These ones?
Yeah, for sure.
Oh, this is generic, essentially.
Okay. So always, but the thing is the time that it will occur, right?
Yes.
Okay.
So if you, where I must have it somewhere. So essentially, this object, roughly speaking, is a sum of exponentials with the transition energies of the bath. So if you sum periodic functions, you end up with stuff like this as long as you have a finite number of them. So this is super generic. But of course, the conditions become more and more, the conditions for doing this become more and more stringent as these energies become small, in the sense that the level spacing is small, and then you can push this stuff. Since the level spacing scales with the number of particles, like 1 over the particle number square maybe, or even exponentially depending on the system, then these recurrence times are moved further. I thought I had it somewhere. So it's convenient to work with the Fourier transform of this function rather than with with the function itself. It's the physical interpretation is clear. So this, I'm going to call this the spectral density. And if you, okay, I'm going to define the eigenstates, the exact eigenstates of the bath. If you do the spectral decomposition on the time evolution of the bath, you can perform the integral, at least formally. And you get this, where these are the Boltzmann weights of the bath. So I'm assuming essentially that the bath is large but still discrete. Then in practice, to actually do anything, you need to have a way of converting this sum to an integral and going to the continuous limit. But for interpretation, this is clear. So this function is quantifying the density of excitations in the bath that are available for the interaction with the system. Indeed, this object has support at frequencies corresponding to excitation energies. This is minus EA, EB. These are the Bohr frequencies of the reservoir. And these transitions are weighted by matrix element of the coupling operator, which of course also embody selection rules, if any. And then of course you have the Boltzmann weight of the initial state. Of course, if the state is barely occupied, then exciting it to higher or lower states is going to have a lower weight because you start with a rare with a rare state. So, from this perspective, essentially, what these conditions of long recurrence times, it means that the level spacing in the bath should be much smaller than the decay rate of the system, roughly speaking. So the system cannot resolve the spectrum of the bath. So these gammas, right, define a set of decay rates, and what I want is that these energies are a set of delta functions, and the gamma is going to appear something like this. So this is, let's say, this is the spectrum of the system, if you wish, because it's not a stable eigenstate, so it has a broadening, and the broadening must be much bigger than the minimal difference of the. And then it makes sense to approximate, to consider this as a continuous function. Now, this function has some. So this is is an extremely generic way of considering of looking at this function. In practice, this is simpler. I'm going to give you examples. There's an important property for what follows. Is that if you are a reservoir at 0 temperature, then of course this weight is going to select B as the ground state of the bath. So that's fixed. And then if you look at this, if B is the ground state, then all the other energies must be larger than the ground state. You can only excite a system in its ground state. So this means that at 0 temperature, the spectral density is 0 for all negative frequencies. So this is the way, let's say, the way the existence of a ground state appears from the spectral density, which means that whatever it is, the system, you're going to have something like this. Start at 0, then does stuff. At finite temperature, you can have, of course, transitions from an excited state to a lower state, and so this thing generally acquires weight at negative frequencies. Roughly speaking, the weight, the transitions here correspond to transitions which the environment is absorbing energy from the system, and these are transitions in which the environment is giving energy to the system. Okay, maybe I can give you an example. If we take our beloved spin boson model, now this is my B operator.
Can I ask something?
Yes.
Yesterday I asked about solid state applications. So if your HS is like a band structure, for example, and you said something about you run into problems when the level spacing is really tiny in HS. Is this already related to the level spacing of the bath, or is this a different problem?
No, it's a higher level problem, I would say.
Okay.
It's going to be clearer later.
Okay.
Because let's say the point is, yeah, the level spacing might be small, but you always have smeared you have a smeared spectrum because you have an unstable states. So this can in principle always help you not to resolve the path. So for this system, the special function has this shape where B of omega is the Bose-Einstein distribution. Of course, zero chemical potential, these particles are not conserved. And rho is the spectral function, which is this object. So these are the essentially these in this case it's clear that you have a subdivision, a conceptual subdivision between thermal occupancy, which are these PB factors, and the actual shape of the spectrum, which comes from this, and it's given by these weighted sums. And this condition that at zero temperature you have zero weight at negative frequencies is given, well, by this, by the properties of the Bose distribution, and also by the fact that for this system of bosons to have a well-defined ground state, all these frequencies must be positive. If you have a frequency that's negative or zero, then you could condense all bosons inside of these states and lower the energy arbitrarily. So if all these omega k are positive, then this object has support only on positive frequencies. And if you plot this, so the typical situation, like in many situations, this function is assumed to behave as a power law for small frequencies. Let's say smaller than some unknown UV cutoff, but let's say close to zero frequencies. This is usually a power law. For instance, alpha equal 1 is the so-called ohmic case, and you find it, for instance, in metals. So whereas alpha equal 3 is the case for the electromagnetic field in free space. So for like the decay of atoms in free space, the situation is exactly like this with so-called super ohmic frequency dependence. That's omega to the third. And if you plot this stuff, you get, for instance, in the ohmic case, at zero temperature, you have something like this. I'm assuming I'm adding a cutoff somehow, so this thing needs to go to zero at very high frequencies, but usually that's not too relevant. So this is zero temperature, and then at finite temperature, you get something like this. So this, you acquire a tail at negative frequencies, and this, the height here grows as the temperature. For super ohmic, okay, we have more stuff, which is something like this at a finite temperature. Whereas at zero temperature, of course, you have something more like this. Okay, these are examples. I'm emphasizing this stuff. Yes?
So here you're mentioning these negative frequency content, which to some level, sometimes they anti-symmetrize this density function to get negative frequencies. But here, they apparently come out of the temperature dependence. I just wanted to know if, like, how should we interpret these negative frequencies?
Is the amplitude for transitions in which the environment is pumping energy into the system.
Like the driven part, rather than just dissipative?
I wouldn't call it driven. It's like the simple fact that, okay, if you have a finite temperature reservoir, you already have available excitations, and it can happen that these excitations dump energy into the system. But this is, I mean, this is required for thermalization at a finite temperature, right? That the environment gives and takes unless until equilibrium is reached.
Okay, yeah, thank you.
So the reason I'm emphasizing all of this is that all these distributions have a non-analytic behavior at zero frequency. So here you have a cusp, here you have zero, and then it goes up to something with a non-vanishing derivative. Here also you have higher derivatives, which are singular. And these singular points are ubiquitous in these objects because real systems have a ground state. So these singularities are a signature of a ground state. If you don't have a ground state, then you might have a completely smooth spectral density, but that's unphysical, strictly speaking. Also, this means that the behavior of C of t, so if you look at real time, it's gonna be generally power law. So, because if you, the Fourier transform of a non-smooth function generally decreases at large times slower than an exponential. This is a general theorem of Fourier transforms. So what generally happens is that, okay, let's take the log of this, is that this system will have an initial exponential behavior, which then slows down to a power law. And typically the exponential behavior is something like, this is essentially a Matsubara frequency. So the decay rate is proportional to the temperature, and then there is a slow power law tail, with an exponent that's directly related to this one. So when I was saying that you have a system with a tau b, you have an environment with a tau b which must be small, it's, let's say, an approximate view, because the true behavior at very late times is actually power law. But this, I'm going to show you that this is not a problem for the Markovian approximation to hold. So you can have a good Markovian dynamics for the system, even if the reservoir has algebraic correlations in time. In this sense, let's say there is only one ideal system that is Markovian always, which is a system whose spectral function is completely flat in frequency, because then you Fourier transform and you get a delta function. So if you have a delta function, you do the Markov approximation, and you end up with Lindblad without any further problem. I mean, if this is, it's not even a Markov approximation, you just get Lindblad for free, and you don't need to worry about all these things about eigenoperators. Yes?
So besides this one, if you take like the ohmic one, but with infinite cutoff frequency, so it never decays, you don't get delta, but you get the derivative of delta, which, do you think that's also Markovian? In some sense, it depends on the previous time step.
No, I would say it's still Markovian, but
But I guess the infinite cutoff
The
frequency
infinite
is
cutoff is
not physical.
I mean, I would say the infinite cutoff is going to give you troubles, but essentially like this, it's probably unphysical. Exactly like this. This is unphysical because this doesn't. This is something for a system which doesn't have a ground state. So this can be at best an approximation. All real reservoirs have a structuring frequency. Yes. Okay. So where is the rag? Okay. So I'm gonna give you a glimpse on how a non-Markovian dynamics will look like. So before doing the Markov approximation, we had this Born master equation. Okay, for the trace, and then system and the initial state of the environment. Now, if, for instance, you take matrix elements of this on the eigenstates of the system, you're going to get something that looks like this. So you get a linear integral differential equation. Let's say I'm hiding a lot of details, but because it's not particularly relevant. But, there's some, as I said, this is linear, so this is a linear operator. It just have more indices because these objects are matrices. But okay, this is just some kernel convoluted with the state up to some time, and this is the kind of equation that you would need to solve if you stick with this Born master equation. Now, there is a particularly simple case in which you can actually solve these kind of equations, which is the simplest one, in which you have only one of these objects. For instance, this could be an equation for a single coherence, so a single off-diagonal element here that evolves on its own. So this is, let's say, a toy model for non-Markovian evolution. This kernel is going to be essentially the Fourier transform of something like this. There is actually, in this case, if you do the rotating approximation at this level, okay, you do some approximation, you have a model whose solution maps exactly like that, in which F is the probability amplitude for the spin to be initially to be excited at time t. So this basically is a very good model for the decay of an atom in free space. Then, of course, for decay of an atom in free space, you have a specific form of rho and hence of this kernel K. But this you can solve this for any kernel that you wish. Now, I had a lot of fun in solving this. It's solvable by Laplace transform, and then you have to have fun integrating in the complex plane. I will spare you that. If you want, there's a review or ask me. It's a very interesting calculation, in my opinion. But okay, you can also put this on a laptop and integrate it numerically. It's actually probably the most efficient way if you want just numerics. So well, let me make a step back. So this is essentially completely analogous to that Born master equation. So in principle, we could just do the same steps that led us here and get a Markovian version of this. The steps. So first thing is going to the interaction picture. So we extract the fast dynamics, which is the unperturbed one, and leave only a slow varying function. And then, sorry, this is exact. Okay, this is exact. Then we can do the Markov approximation. It's the same reasoning. This, we assume that this object is decaying sufficiently fast with respect to the time scale of decay of f tilde. So this is a slowly varying function, whereas this is fast. Also, this is fast. So essentially, we pull this out of the integral. And if you look at this, you should see that it's basically the same object. It's one of these big gammas. So this is essentially and this is, let's say, the equivalent of red field for this toy model, which can be solved. Let's say we can even do the full Markov approximation. So we just, again, invoke the fast decay of this object and push the integration here up to infinity. So we just get some asymptotic rate. And this is, of course, an equation for an exponential. So if you put everything together, in the Markov approximation, you get this, which, as I showed you yesterday, the solution of the Lindblad master equation or the red field is just a bunch of exponentials. In the true equation, this you have d square of these objects, so you can have up to d squared rates. Here you just have one object, so you just have one rate. And this rate is a complex object, so you can just separate it in real and imaginary part. Yes. So this is, the real part is the lamp shift, and the imaginary part, sorry, the imaginary part is the lamp shift, so it's just renormalizing the frequency, and the real part must be negative, but it is, and you can prove it is, and this gives a decay. In the same way as the imaginary part of the gammas here gives a Hamiltonian contribution, and the real part is associated to decay. And if you assume that these k is given by a Fourier transform of this of a certain spectral density, then this gamma Oh, sorry. I'm using a notation, which is, yes. This is omega naught. So this is the lamp shift. So this is the imaginary part of the gamma, which is just a renormalization of the frequency of the system, of the amplitude frequency of the system. And okay, it's a principal, the principal pulse of an integral. This object is generally sensitive to all frequencies, and it's, let's say, to really predict this object, you need to have a good theory of the bath, because otherwise, if you just put random cutoffs here, you're gonna get stuff which has unphysical features. So it's generally, let's say, thought to be reabsorbed in the omega naught that you actually measure. And then you have the real part, which is the decay rate, and it's negative, and it's just the spectral density evaluated at the system frequency. So when I say, okay, the Markov approximation for this problem, which is the baby version of the Markov approximation we did yesterday, has some specific predictions. We have a certain, we expect to see damped oscillations in the f function with a certain rate that we can predict in this approximation. But this model can also be solved exactly, so we can compare the two and see where they match or not. And the result is this, as this shape. Again, I'm plotting a logarithmic scale, so whenever you see a straight line is an exponential. We start at a certain non-zero value. Is a function of time. Okay, the plot is not ideal. Maybe more precise. Okay, so the outcome of the calculation is that there is an intermediate time window in which this is actually exponential like that. Sorry. Well, there's a minus. Okay. So this is the region, the region of validity of the Markov approximation, and hence, essentially, you can expect the Lindblad master equation for this object to be valid, not at very early times, but not even at very late times. So at very early times, you have a parabolic behavior, which is the one you find also when you look at the Zeno effect. And this is, let's say, a weakly non-Markovian effects, in the sense that at very early times, you see that this object has not decayed enough. So this correlation function is still not fully decayed. So you just, the system doesn't see the full version of the bath dynamics and relaxes more slowly. And this is true also for the linear master equation. If you want to do predictions which occur for stuff that occurs at very early times, you need essentially to keep the time dependence in this object. So here I put infinity, but you need to keep the time dependent. And indeed, if you take the derivative at 0 time of this, you generally get a non-zero value. Whereas the true dynamics, which is this one, starts at 0. Again, this is a small transient, if you wish. So in most of the cases in which we are interested in, let's say, the steady state of late time dynamics, we don't care about this, but it's there. It's a weakly non-Markovian effect. It just, there's a remnant of a notion of an absolute time here. It's not a matter of like the environment feeding back stuff to the system. So after this transient, the Markov approximation becomes effective. And so we have a long stretch of exponential behavior. And this typically lasts for a very long time, maybe in tens of relaxation times. So at the end of this region, the function has decayed almost completely, but not completely. And then possibly with there is a transition region, and then at very late times, this crosses to algebraic behavior. Now, this algebraic behavior came to me at least as a surprise when I first learned about all this stuff. It's a universal phenomenon in the sense that it occurs generically for quantum systems, because essentially you can prove that under unitary dynamics, a purely exponential evolution of an amplitude is forbidden. So a state amplitude can decay exponentially, but after some times, it needs to switch to something different. And that something different is a power law. And so this has never been measured for an atom or a subatomic particle, but it's, in principle, this happens whenever, I don't know, a neutron decays or whenever an atom emits light. But since this happens at very late times, it's very hard to get enough data against noise in this region. But slightly less than 20 years ago, this was observed first with organic dye molecules. You can find it on PRL. So let's say this has been verified also, but it took some time. So, okay, and then this. Yes. Yes, this is what I'm about to comment. The full so this behavior can be put into in contact with the properties of this spectral density, J omega. So this I'm assuming something like this at 0 temperature, so it's 0 at negative frequencies, then goes up, and maybe decays at very high frequencies. And so, okay, at very early times, the dynamics here is sensitive to all frequencies. So again, it's a non-universal behavior because you need to know the details of all that's happening in the spectrum of the reservoir. But it turns out that the properties of the Markov regime are determined only by the properties of the spectral function around the neighborhood of the system frequency. So the system is essentially probing the excitations of the environment only in a narrow region, and the width of the region is essentially the decay rate that you measure. It's, well, if I write this, and the decay rate is this object, or the real part of that gammas over there. So indeed, for instance, the decay rate itself is determined by the value of the function of the spectral density at that frequency. Whatever happens around here in this intermediate regime is irrelevant. Vice versa, if something drastic happens here, then you're going to feel it. And basically, what happens is that all these power law behaviors are caused by non-analytic points in the spectral density. For instance, if for some reason here you have a cusp, so the derivative changes abruptly, then you would essentially lose the Markovian behavior and start behaving as a power law as soon as you pass the transient. Or vice versa, if this thing has a peak, a very narrow one, then the decay rate is going to be the width of the small peak rather than the height of the peak, which is this prediction. So all of this to say, for the Markov approximation to hold, the spectral density must be smooth around the frequency of the system. So this is essentially the quantitative or semi-quantitative condition for the validity of the Markov approximation. If the derivative is too steep, then you start getting corrections to this to the predicted value. Or worse, if you have non-analytic points, then you would destroy completely Markovianity. Vice versa, it could be that you have weird stuff happening here, but as long as the frequency of the system is not probing the bath where weird stuff is happening, then even a bath with a weird spectrum will have a Markovian dynamics. So in this sense, saying that a bath is Markovian, it doesn't mean anything. A bath might be Markovian around the system frequency. It's a relative property. And all this thing about power laws and non-smooth points is the precursor to what is happening here. So, yes? The level spacing. Yes, this is the Bohr frequency. So, I mean, right, is the big omegas I'm using there. I'm using a slightly different notation. It's this is a transition that's induced by the bath, and you just need to look at the spectrum of the bath around that frequency. I mean, it's also a self-consistent thing because this gamma is the height of this function. So essentially, if you wish, you need to have a spectral function that is wider than its high, than its tall. If you have a very narrow one, then you cannot expect to have a good Markovian regime.
So if the level spacing of the system goes to 0, then it's not Markovian because you have the non-analytic point at...
Yes.
Okay.
Yes, that is exactly the point. So, as I was saying before, spectral densities generally have at least one non-analytic point, which is 0 frequency. And this is, again, connected to the fact that a realistic bath has a ground state. So this is basically unavoidable. You might have other things, for instance, maybe you have many bands, so you have gaps, and also those are non-analytic points. But there's, let's say, at least one non-analytic point which is guaranteed, 0 frequency. And again, if you assume that the behavior is something like omega to the alpha, then this is the exponent that you get at very late times. So this tail occurs when the Markovian part of the dynamics is completely gone, so that you start seeing all the edge effects around here, all the non-analytic points around the frequency. And again, this is unavoidably connected to the existence of a ground state. So in this sense, this is unavoidable for realistic systems. Maybe you'll never observe because it's too late in time, but in principle it's there. And if you can derive some equations that govern more or less this behavior, and it's not obvious to have an intuition on what's happening down there, but roughly speaking, it's a kind of a quantum version of recurrences. So there's, the system is emitting excitations in the environment, and these excitations always have a very small tail at the position of the system. So at early times, you get the leading Markovian behavior, you don't notice them. But at very late times, let's say there is enough, when there is enough time, these tails make always possible for essentially the system to return in initial state. And this is again, it's completely quantum, and it's not related to the fact that the bath might be finite size. All of this works because I'm assuming that J of omega is a continuous function. So this bath is a continuous bath as a continuous spectrum. Okay. So this is somehow meant to provide a more realistic conditions for Markovianics. So when you're deriving a Lindblad treatment for the system that you're studying, you should compute the spectral density of the bath and see what are the transitions that are induced. You look at the frequencies of the transitions, you look at the spectral density around these frequencies, and if nothing bad is happening there, then you're fine to use the Lindblad master equation, essentially. Or at least the Redfield one, unless there are other surprises on the way.
Would if your bath was particle hole symmetric, would you still have a non-analyticity? I mean, maybe that's a pathological example for a bath.
I mean, fully one extending from minus infinity to plus infinity.
I mean, just on the level of a spectral function, particle or like chiral symmetry or particle hole symmetry means that it's symmetric
around zero.
Around, right? So.
But generally, especially if you have something like more solid state in mind, you have band edges, typically. Unless you have a band that spans the whole real axis, but then it's a system without a ground state.
Yeah, I mean graphene, for example, as a bath, right? I mean.
Well, but okay. Sure, around the direct points, yes. But let's say real graphene as a bottom of the band. That's the point. In that case, that thing is actually the bottom of. At some point, you will have. You will feel the bottom of the band. Again, this is probably happening if the bottom of the band is very far from your frequency, then of course that no Markovian regime, you can basically forget about it because it's going to happen somewhere, I don't know, hundreds of decay times. So you don't really care. The system is already decayed. Everything already happened. But in principle, it's there.
Okay.
Yeah, actually, especially for fermionic systems. So for bosonic systems, you have this picture in which essentially it's natural to assume that the only non-analytic behavior comes from occupation factors. For fermionic systems, usually you have a bandwidth also. So this thing does not extend arbitrarily high and low in frequency. You have another cutoff. And band edges are another sort of non-analyticity. But that is intrinsic to the spectrum.
Okay. Thank you.
Yes.
Sort of to comment on that discussion, even if you have a symmetric distribution function, which would be the particle hole symmetry case, you can have the non-analyticity in the second derivative. So it could be continuous, but it could still have a non-analytic point. And in fact, if you have an exponential cutoff, even if you have linear dispersion at zero frequency, you will get a non-analytic second derivative, which somehow has information about the tails of the distribution.
Yes. Other doubts, questions? Okay. Half an hour. Okay, let's like, okay, for instance, since you're more interested in, let's say, solid state applications, what if you have like a fermionic bath, or let's say the thing that you have there so the spectral density is going to look something like this. So you have some band, so you have the band edges, and this comes essentially in the notation for bosons, which I erased very conveniently. But you have some spectral factor, and then you need to account for the Fermi distribution. And so this will occupy the low energy and then have a sharp decrease. So, for instance, in this system, this is like that would be the case of very low temperature, and this system can display this environment can give rise to Markovian behavior as long as the frequency of transitions are around here, so far from the Fermi surface and far from the edges. If you stay very close to an edge, then you will see the edge, which is an analytic point, and you get power law. If you stay too close to the Fermi surface and the temperature is too low, then you will see this very sharp behavior. And in the best possible scenario, you just get corrections to the Markovian rate. But again, you cannot trust Lindblad because you only get the Markovian rate in the Markovian approximation. Or you need to hope that you are very high temperatures so that this gets smeared out and it's benign. Yes.
But what do you mean with, I mean, you have like a single band and you have, then any transition, if you stay in this band, your transition must somehow pump momentum into the system, right? But then your level spacing will be just like vanishing with the, so wouldn't it always be at zero?
When I say fermionic reservoir here, fermionic means that the operator B must be fermionic.
Okay, but
so
what
it's
is
a
omega
bath
zero?
that is exchanging particles.
Oh,
if you have a bath which is coupled like through density to an interaction, then the bath is actually bosonic because the excitations will be particle or pairs, and basically that pictures become valid again.
Oh, so
this
omega,
is actually the case.
So omega zero would be the work function, like the amount of energy it takes to take out a single electron.
Omega zero, no, omega zero is, I don't know, whatever are the frequencies that are, whatever is the transition frequency in the system. That depends on selection rules, depend on the spectrum. It's probably going to be small in realistic situations, but let's say this is more of a, I mean, this is more like, I don't know, a qubit embedded in a metal.
So omega zero would be a transition to another band, for example.
Yeah, if
Okay.
that's an allowed transition, sure.
Okay. Thank you.
Okay. Now I'm going to give you a couple of examples physical examples in which you can see how the Markov approximation fails more or less miserably. And it's all a game of computing spectral densities. So, as I said, if you have your two-level atom embedded in vacuum, the electromagnetic field is going to give rise to a super ohmic distribution at all frequencies in principle, and this is a sufficiently benign distribution in the sense that as long as you're not probing this too close to zero frequency, I mean, there's of course like a Heaviside function. This starts at zero and then goes up. But as long as the frequency that of the atom is finite, everything is fine. You get a nice Markovian behavior. Actually, the decay of atoms is very Markovian. You do get a power law that is 1/T⁴ at very late times. This is known since, I don't know, the 60s, I think. But it's never been measured in practice because it occurs too late. But then there are situations in which you can alter, I mean, let's say the origin of this behavior is the dispersion of photons, which is, of course, linear in momentum. So this is, let's say, linear dispersion plus three-dimensional space. Now, you can alter the dispersion of photons by, for instance, putting them inside of a cavity. So in a cavity, you have, of course, quantization of the electromagnetic modes. So if you look at the spectrum of this, you're not going to get a nice, smooth polynomial, but you're going to see a series of peaks at the resonance frequencies of the cavity with a certain width which is determined by the quality of the cavity. Now, when you see a spectrum that it's made of peaks, you should be careful, because if you end, for instance, if the peak is very sharp and you're probing at a frequency, so you imagine you have a two-level atom embedded in a cavity and you're trying to see the decay of this atom. Well, if the peak is too narrow, so the condition of the spectral density being smooth around the probing frequency is going to fail. And you're not going to see Markovian dynamics. What happens in this case is that basically you emit a photon, the photon remains in a cavity, gets reabsorbed, and the process repeats until eventually it leaks out of the cavity. So these oscillations can be seen, and they're a signature of a good cavity. But in this case, essentially, the correct approach is to include the photon as part of the system, because the rest of the universe is still omega to the third, and it's a good reservoir. Instead, if you have a very bad cavity, the peaks are very broad, and then you can actually have Markovian behavior. And this is known for very bad cavities. You can essentially integrate out the photon and treat it as part of the reservoir, and you get a dynamics which involves only the matter inside of the cavity. But you can also have situations which are in which the modification to the spectrum are even more drastic. If you have a system in which you alternate layers of material with different refraction index at a spacing comparable to the wavelength of light, then you can have a photonic crystal. So the dispersion, the linear dispersion of light gets, I mean, you have a periodic structure, so you need to look at the Brillouin zone, and this dispersion is folded into the Brillouin zone, and a gap opens. So this is exactly like bands in solids. But you can have, I mean, a crystal of photons. So the dispersion becomes gapped at the edges of the Brillouin zone. This means that if you look at in frequency around here, you have something like this. The spectral function goes abruptly to 0, remains 0, and then grows again. So if you happen to put your atom here, so if you choose the parameters of the photonic crystal such that the gap occurs around the frequency of the atom, then this atom is going to decay in a very non-Markovian fashion. Why? If you look at this picture, Markovian decay is caused by resonant transitions, because here there's a lot of excitations which have a frequency close to the frequency of the system that are excited at the same time. If you are completely non-resonant, so you are probing the environment, in a region in which there are no modes to be excited, then decay will proceed with the nearest available modes, which are, however, band edges. And whenever you have band edges, you're going to have no Markovian behavior. And this is known since the 90s, and it's also been verified. So people have actually measured the decay rate of this. And you, let's say, if you take the excited, the probability of the atom being excited, what happens is that it oscillates a bit, but then it never decays. So you can actually prevent decay completely. And what is actually happening in this case is that essentially the photons here are so slow that they form a bound state with the atom. So the system is actually relaxing to a bound state. And you cannot predict a bound state with second-order perturbation theory. So all this machinery here fails completely in this case. When you start moving the atom inside of the band, then this curve will start to go down and relax. And if you go deep enough, then the system will not see anymore the band edge, or essentially, it's going to be like this. So this is the band edge. If you go enough like this, you will not see the edge anymore, and the decay is going to become mostly exponential again. Of course, at very late times, again, you have the Paolo behavior and so on. But yeah, it takes a while to, let's say, remove this residual occupancy, which, by the way, cannot be predicted within Lindblad. You need to either use an exact equation, or you need better approximation, because essentially this is non-perturbative as a phenomenon. Whenever you have a bound state, this is non-perturbative. Yes. Let's say, as a general, let's say, as a rule of thumb, if you do all this machinery, you compute these rates, and you find that the predicted rate is 0, you should be careful, because you're probably going in a regime in which you will see no Markovian effects. So that's a useful warning. So the final example for more solid state stuff is the Kondo model. We had a glimpse in a talk yesterday about what is the Kondo model. We have a spin 1/2 impurity that interacts with a bath of fermions, and the Hamiltonian is actually quite simple. So this is free fermions, and this is the bath. This is my impurity. And this small s is the density of fermion, sorry, the spin density of fermions at the position of the impurity. So this is a very famous model if you're doing solid state. I mean, the details of this are maybe not important, but maybe if you've never seen this, it makes more sense in this way. So this is a model which has been solved, so there's not much mystery left, but it's a famous example of a strongly correlated model. And so this would give you a hint that Lindblad cannot work here because Lindblad is only perturbative approach. Now, this is a model in which the system has no dynamics on its own. The system is a spin, but the spin is isolated. Unless you put a magnetic field, the system the spin will not do anything on its own. There's only the bath and the interaction. And let's say that the lambda is essentially this one. And still, you could think of being reckless and try to apply this machinery. And well, in this case, the three components of the spins are constants of motion, so they're automatically eigenoperators. The jump operators are going to be the three spins. Let me see if I don't. Yes. These ones are the spin components, sorry. Sigma and tau are up and down for the spins. These ones, you mean? Oh, this is the Pauli matrices. Literally, this is the matrix. The spin alpha is Pauli matrices. Sigma SZ is sigma Z element sigma tau, where sigma and tau are up and down of this. I mean, this is not particularly relevant. If you're curious, this is the expression, but I'm not going to use this. It's for completeness. So you take the correlation function of this object, you take the Laplace transform, and you can compute a decay rate of this. Actually, there's a nice thing that can be done. Basically, this sum can be simplified, and thanks to the properties of spin operators, these are spin 1/2 operators. So the result is actually much simpler. This, I put gamma L as Lindblad. So this is essentially saying that you expect the system to relax exponentially to a maximally mixed state. The maximally mixed state would kind of make sense. We expect to find the Gibbs ensemble, right, of the system, but the Hamiltonian of the system is 0. So this is automatically 1. So this might look like it's a sensitive thing. However, when you do the calculation, you find that this decay rate is proportional to the temperature. And in particular, so the prediction of Lindblad is that if this environment is at 0 temperature, nothing happens. The spin remains frozen in initial condition and never changes. Now you look at the exact solution of this, or let's say better method that allows you to work out the dynamics, and you will find that actually there is a zero temperature rate of decay, and it's given by the so-called Kondo temperature. So in this system, essentially, due to quantum fluctuations, the spin relaxes even at 0 temperature. So in this case, we obtain a dynamics which looks kind of reasonable, but we end up with a blatant contradiction that this spin will never relax, whereas in fact it relaxes. Now, what is happening? If you look at the correlation functions of this and their spectral function, it will look actually like an ohmic reservoir. So the at small frequencies, the spectral function is actually, yes, it's a linear function of frequency, which means essentially at small frequency, there's a lot of excitations available. And this is true. Metals have our gapless system. It takes a very small energy to excite a lot of particle pairs across the Fermi surface. And the transitions induced in by the bath into the spin are at 0 frequency. So this probing frequency is exactly at the non-analytic point at 0 frequency. So this is why the dynamics cannot be given accurately by this. And it's actually non-Markovian, although if you look at the numerics, the true dynamics is still exponential in time. But the rate is given by something that's completely different from what you predict here. Only if you raise the temperature well above this Kondo temperature here, then the spectral function smoothens out. And then the fact that you're probing the system at 0 frequency is no longer a problem because you acquire a finite spectral density. And basically this result becomes actually applicable. This is known as the Koringa rate in the literature. And it's actually what you measure even in Kondo systems as long as the temperature is big. These Kondo temperatures can be, I don't know, a few kelvins, so it doesn't take long. But if you're really interested in the dynamics in the full quantum regime around 0 temperature, then this is definitely a no-go. The dynamics is not Markovian, and Lindblad cannot be applicable. Still, again, this is a word of caution, because if you you can still derive a Lindblad dynamics which looks perfectly reasonable. Actually, even the fact that you get the steady state is presumably correct in this regime. The true steady state at 0 temperature, the true system, the true ground state of the full system is a spin singlet, in which this spin forms a singlet with the rest of the bath. So if you trace out half of a spin singlet, you actually get the identity. So this is even correct. But unless you start, unless you are very careful and you look in frequency and you notice that you're probing the system at a frequency which cannot possibly be Markovian, this formalism will not give you any warning signs if you're very, let's say, mindless. A warning sign, a typical warning sign, which was the early warning sign that something odd is happening, is that if you try to get higher the corrections, so you go beyond this second order treatment, you will see that this rate starts to acquire logarithmic corrections, and the fact that this log diverges at 0 temperature is telling you that the system is actually strongly coupled. But again, this is if you wish, essentially you can verify that even solving the Born-Master equation doesn't help. If you solve the Born-Master equation, you do get decay, even at 0 temperature, but it's non-exponential, so it's wrong, because the decay here is known to be exponential nevertheless. So what it's really breaking up is the first of our hypothesis, so that the entanglement between the system and the bath doesn't play a role. Here it does all the heavy lifting. So all the decay is given by entanglement. So this approximation is completely wrong. And again, you can argue, like in this sense, like in this problem, that you're basically dealing with a bound state between the spin and the rest of the bath. And whenever you have bound states, this Born-Master equation doesn't work. Yes?
But the approximation was that only initially there's no entanglement, right?
No, sorry. The point is true, but let's say this is an assumption that you have an unentangled state, which you can do also in the Kondo model, of course. But the point is, the Born approximation is that, okay, I keep this non-entangled structure, but I'm dressing the density matrix. So the density matrix here is the time evolving one, the interacting one. Of course, this is not the state of the system. You also have corrections which are non-separable. But the Born approximation is the assumption that these non-separable corrections are actually higher order and do not matter, of course, if you're happy with a low order treatment. But in this case, this bit here at 0 temperature is giving you nothing. There is no evolution. And then the higher order terms, which are entangled, are the ones that drive the dynamics. So it's a completely non-Markov and non-Born dynamics. You have to resort to other methods which do not go through this. There is, I don't know, personally I'm fan of field theoretic methods, and you can just, and if you're doing field theoretic methods like Green's functions, 2pi and so on and so forth, you can just simulate. I mean, there is no real need of like tracing out the environment. You can just simulate the full unitary dynamics of system plus environment, and you don't need to worry about Markovian, non-Markovian stuff, because everything gets as the same shape. Let's say it's a formalism that naturally works deals with non-Markovian objects with a complex structuring frequency. So this is an option. Indeed, well, for Kondo there are specialized methods. Numerical renormalization group, Pullman scaling. Yes, the dynamics is mostly a numerical renormalization group. For other stuff, well, it's really obvious how to deal with non-Markovian systems. Not exactly in this simplified. There are people who propose non-Markovian master equations. So equation that somehow keep the structure, and you have some kernel that you can compute, or it's hypothesized. But I think at least in these cases, I'm not sure that these cases would work actually in this specific example, because Born is always is problematic. Okay. I think this is all I wanted to say about the macro approximations. So if you don't have any further questions, we can go and have lunch, I guess. Thanks.